Hello, thank you for joining us as we present our project on the development of blimp UAVs, playing aerial soccer game, actuation, and control. First, the problem we are trying to solve is to explore the development of lighter-than-air UAVs to have features to manipulate objects through the stage of a soccer game. In this project, we aim to have teleoperated blimps that can fly and play a soccer game with the ball against other opponents for at least 1 hour and have no more than 50 cubic feet of helium per agent. We created specialized offensive and defensive capabilities that consist of modular features that can be taken off or put back on. We will go over these features later on in the presentation. Our blimps are based on the principle of buoyancy, in which the lower density of the internal gas, which is helium, lifts the blimp. We utilize non-rigid blimps for compactability and transport. All electronics are all in the gondola position, such that the vehicle's center of mass is located below the center of lift to allow for passive stabilization. Electronics rely on radio frequency data communication for distance operation of the blimp. Next, we will have an overview of our approach that we scaled down due to COVID. From this diagram, we see that our design has user input to teleoperate the blimp with the microcontroller, controlling the various specialized actuators we developed in order to manipulate the ball into or away from the hoop. In the functional decomposition overview, we see that data is decoded to actuate the motors and servos to provide the desired movement. In our blimps, we have a motor and propeller in the back for forward and backward thrust, and a motor in the bottom center of the blimp to provide lift or descent. Servos direct the back motor for turning.
Next, we have several developed defensive and offensive capability. For the defensive capability, we designed a net welding blimp. Essentially, our first design has a polypropylene net that is parallel to the blimp with carbon fiber rods at the top and the bottom to spread the net. The game size ball is 24 inches in diameter, so we calculate the max size of the net hole to have a minimum amount of net, yet still be possible to block the ball with a hole of 11.4 inches per side of the square hole. But we used a smaller ball of 18 inches during the demonstration, so we went the hole size of 8 inches at each side of the hole. We also have alternative design for the defensive blimp with the net being perpendicular to the blimp. This design is better for going after an opponent and jamming the blimp into the goal so that no one can score. However, it's not as good at screening the goal, which is essentially going up, down, right, left in front of the goal. In addition, the parallel net seems to give extra stability in comparison to the perpendicular net replacement. It can be said that different designs are better for different purposes. For offensive capability, we have several passive and active designs. The passive design is a cup mounted on the front of the blimp with glue trap to catch the ball. In a previous blimp flying test from our group, we found the collision between offensive devices and the ball because the ball just bounced away. So we solved it by using modified bug-catching glue traps, which can disperse the energy and secure the ball. After our testing, the cup can catch and secure the ball, and it's lightweight and modular, which are useful for adjusting the weight of our blimp. The other offensive design we have is the interfering fin. It's a bundled fin mounted on the front of the blimp. The fin has the same glue trap for attachment. When the fin is attached to an enemy blimp, it will release and then fuel. It causes the enemy blimps to constantly turn. While the fin contraption is only 1.5 grams, our tests show current weight may be small enough to not cause too much buoyancy change. We currently have the blimps be neutrally buoyant without attachment, such that the blimp can rush to the enemy while overloading, attach the fin, and then be neutrally buoyant for the rest of the game. Currently, the interfering fin is released passively by colliding with an enemy blimp and jerking away. One of the active offensive design is the grabber. The two pictures are the 3D model and the assembled 3D printed parts. To activate the devices, the motor in the tail can gear the trap stick in the middle, which causes the four large gears on the front revolve, and then the rods on the gears will be open or closed. Originally, the devices we designed was used to grab the ball with the rods on the gears, but with straight rods, it will push the ball away when it's closed. So we changed our thought to shoot the ball with the straight rods on the gears and instead use a sticky pad between the gears to catch the ball. This is our test of pushing. We also tested while mounted on the blimp. It turns out we need a gear set to increase the torque in the tail to release the ball from the glue trap. The total weight is heavier than passive designs, and the short straight rod becomes the guide for releasing the ball. We have another alternative offensive pushing design. We keep the sticky pad steady in the middle to control the ball and use the sidearms with bumpers to push the ball off for release. It's similar with the claw design without the guiding arm. Therefore, the total weight is better than the previous design, but in our test, it cannot guarantee the direction of pushing.
Microcontroller evaluation. For our designs, we worked with the ESP32 and the Raspberry Pi Zero W. The ESP32 comes with integrated Wi-Fi and dual mode Bluetooth, so using its BLE feature, we were able to interface with a smartphone or a joystick controller to provide the user input. The Raspberry Pi Zero also has built-in Bluetooth and Wi-Fi, so we could either interface a joystick controller using the Pygame library, or interface a controller through the Wi-Fi module and use computational key commands. For our ESP32 based blimps, we designed an SMD PCB that features two motor drivers, onboard programming using the CP2102 chip and the micro USB ports, as well as LED indicators for power and programming. After soldering all the components on the board, it weighs about 6 grams total, and this is what it looks like. Although our first PCB design works, we did encounter a problem with our onboard programming method. Due to some strict design constraints that were not satisfied, our board requires some other method of programming, and that was the USB to UART TTL module that is shown here. And so after resolving this issue, we modified our schematic and our PCB design for one final PCB that is shown here in the form of 3D views of the top and the bottom. For our Raspberry Pi based blimps, we decided on a direct soldering method by using some jumper wires and interfacing the controller through the Wi-Fi module, as well as using the computer keys for the commands. Here we can see what it looks like when mounted on one of our blimps and a simple schematic showing the connections.
Hey, Will here. First off, we're trying to figure out how to make the blimp more stable, both inherently and to give it dynamic stability. We made it stable just when it's sitting around by adding mass to the bottom of the blimp so it can recover from any disturbance or outside force. Dynamic stability was more difficult. There, the pictures you can see the fins as well as our cone shroud stabilizer. Those are for keeping the blimp on course if it's moving and then is disturbed. This next experiment is about controlling altitude, which is a problem for pretty much all lighter-than-air vehicles. It's especially tricky. We started off with a movable mass feature to control the pitch angle of our vehicle, and then use the thruster to change altitude, but it was much easier to add a second thruster oriented vertically to control altitude this way. And then for the pilot inputs, since these were going to be remote controlled, we started off with our first prototype taking commands from a keyboard, way too slow. We upgraded to smartphone control using a touchscreen instead, basically. Again, still too slow, even though it was better. The best we could do is with the joystick control, much more natural, taking a range of values rather than a discrete on-off switch to control the blimp.
Experiment 1, power consumption. In this experiment, we have 3 different modes measuring voltage, current, and power to find the theoretical endurance, and as well as we measured the actual endurance in the experiment. For these endurances, we want over 60 minutes so we can play a full game of 60 minutes. First mode, normal mode or idle, is just running the Raspberry Pi, and we found that it was easily could be ran over 2 hours and still had enough battery, so we just stopped it and said this would be successful since it's over 60 minutes. Full speed mode, or running the back motor, since that drew the most power of the blimp, we found it to get 62 minutes and 46 seconds, so this was even sufficient. And then max draw mode, which is the in-game conditions or best ability to have an in-game condition, we only got 52 minutes and 48 seconds, but this was within 15%, even though it was unsuccessful. So this was fine due to This was running the motor pretty much non-stop, and in an actual game you would not be. And this was using a 3.7 volt, 1000 milliampere hour powered LiPo battery.
Will here for 2 more experiments. First one I'm talking about is our defense capabilities test. This one we just straight up played the game and counted how often we were able to block the goal. I was the pilot here, and game 1, 2, and 3 there is sort of like a constant improvement there, defending successfully more often, preventing more goals from being scored. Dinesh had a pretty good blimp, but I had some experience flying blimps, planes, helicopters in the past, which definitely helped me out there. On to just a simple mobility test. We were figuring out how fast we could go with or without a balloon grabbing device on the front. We were slightly faster without it, but we flew just fine with it.
Experiment 4, active offensive capability test. In this experiment, the active offensive capability was timed for how long it takes for it to grab the ball, guide it to the hoop, and score. As you can see a picture here, this is what it looks like. This would be deemed acceptable if it was at least 5% faster than the active offensive capability. As you see in this chart, you can see the module time to score and the non-module. So as you can see, this module is a lot shorter. It was around 13 minutes and the other one was 24.7. So it's almost twice as fast at scoring. Two-tailed T test verified this. So that deems this a successful implementation. Experiment 4, active offensive capability test. In this experiment, the active offensive capability was timed for how long it takes for it to grab the ball, guide it to the hoop, and score. As you can see a picture here, this is what it looks like. This would be deemed acceptable if it was at least 5% faster than the active offensive capability. As you see in this chart, you can see the module time to score and the non-module. So as you can see, this module is a lot shorter. It was around 13 minutes and the other one was 24.7. So it's almost twice as fast at scoring. Two-tailed T test verified this. So that deems this a successful implementation. Experiment 5, communication. In this experiment, the communication between the blimp and controller were tested till failure, meaning until they lost connection. It would be deemed successful if it was more than 50% of the manufacturer's range, at 50 feet. The average distance that we measured was around 74.1 feet until it lost connection. So if you look, the result was different by 8.25 standard deviation, which was enough. So if you look at the chart here, is well up beyond, or 24 feet beyond, the minimum. So this communication met the necessary range required. Funds spent and man hours. So in this we separated into 6 categories: testing the blimp stability and controllability, 3D printing, ESP32 and Raspberry Pi control, offense and defense capabilities, and demos, with the previous semester added on. Offense and defense capabilities right here. So the main one we did 66 hours, and you can see we implemented different offense strategies and defense strategies. But then the total time was 364 hours, and the total funds was $1,491.48.
Hello, this is Romani. I will take it from here. In this slide, we are showing the overall cost breakdown for the whole design. And as you can see from this slide, we have the 2 major components, which are the 3D printed part and ESP32 along with Raspberry Pi, and each of them costs about 22.5% of the whole design. And the cost for the whole design, it costs us about $1,500, including the man hours. In this slide, we are showing the per blimp cost breakdown, which it costs us about $109 for each blimp, which is significantly cheap comparing to the slide before that. The reason behind that, because we have done a lot of testing and part changing throughout the design process. In this slide, we are showing the team member contribution. So we work it as a team group here. In this slide, we are showing the lesson that we learned. We have learned about the component and part selection, stability and controllability of our blimp, advantage and disadvantage of the vertical thrust over the movable mass, design consideration of the power consumption. Also, we learned about the various forms of the interfacing and wire communication. And we did learn about the design of the 3D printed parts. Also, we did learn about the SMD, which is the service mounting device for the PCB design. And to conclude our presentation, we have the references here. Thanks.